Yes, class, is this audible?
Yes, ma'am. Good evening.
Good. So in the last class, we had did this electric field due to infinitely wire, no? So what was the formula that came out? What is the electric field due to infinitely long wire?
Lambda by 2 pi epsilon naught times r.
Times r. So it is E is equal to lambda divided by 2 pi epsilon naught small r. So yes, Akifa, tell me, how does electric field varies with r in case of infinitely long wire?
Yes, ma'am.
How does E means electric field vary with r? How does electric field vary with r? R is the distance, this radius.
It is inversely proportional.
Inversely proportional, correct. So see, we had done this first application of Gauss theorem. It said that electric field due to infinitely long wire is lambda divided by 2 pi epsilon naught r, where E is inversely proportional to r. So as we had discussed that we choose a Gaussian surface first. Why do we choose a Gaussian surface? The reason is that because we have to enclose the charge. In case of Gauss theorem, only those charges which are enclosed within the closed surface are considered for Gauss law. All right. So first case we had studied. Let's do one more case. We had taken infinitely long wire. Infinitely long wire means what? The wire is infinitely long. This wire is extending up to infinity, plus infinity to minus infinity. It's just that I have taken up a portion of this wire, middle portion of this wire, and so as to enclose all the charges present in it, I have wrapped it around the cylinder. All right. Now I am considering electric field due to plane sheet. Electric field due to infinite plane sheet. So infinite long wire we have seen. Now we have to see infinitely plane sheet. So infinitely plane sheet means what? I have taken a plane sheet which is extending from plus infinity to minus infinity again. But so as to ease my calculation, I'll be just considering a portion of it. As in, if this is a very long sheet which is continuous, I'm just tearing a bit portion of it. I'm just considering the central portion of it. So just to calculate. So it has all the charges present on it. And let's say S is the surface area of it. S is the surface area. Now see, Gaussian surface in case of electric field line due to long wire, we had taken a cylinder to wrap the wire. Now see, in case of this, what will be the Gaussian surface that I'll consider? See, I'll just draw a cylinder which will be passing from it. Means this circular part that will get cut when the cylinder is. Like this is your plane sheet. I am drawing the Gaussian surface in this manner through the sheet, penetrating through the sheet. Now this is my Gaussian surface now. Again, it's a cylinder, so it has three surfaces. Two are those flat surfaces. One is the middle curved part. So this is the cylinder. Now see, electric field due to this positive charge will be directed away from the charge. Electric field is directed away from the charge. No. Now see, the three surfaces. This is the first surface, this is the second surface, and this is the third surface. These are the three surfaces of a cylinder. So if I talk about the third surface, yes, Fatima, tell me, what about the third surface? Where will the area vector be pointing? Towards the left, towards the right, upwards, downwards? Fatima.
Towards the right.
Towards the right. Perfect. See, area vector is just a perpendicular dropped on the surface. So if this is the flat surface that I have, perpendicular to it will lead me in this direction. So this is area vector. Electric field is also directed along x-axis. Now area vector is also directed along x-axis. So what is the difference between them? Means what is the angle between them?
0.
0 degree. 0 degrees. All right. Similarly, if I talk about this surface, n cap will point out in this direction, means toward the left hand side in this manner. If I drop a perpendicular to the flat surface of the first curve, first circle, it will lead in this direction. Now see, electric field is directed in this right hand side and your area vector is directed towards the left hand side. What is the angle now?
180 degree.
180 degrees. Now, what about this curved surface? If I take a very small portion of this and if I drop the area vector will be upwards because this is the surface perpendicularly, it will lead in this direction. So now what is the angle between area vector and electric field?
90 degree.
90 degrees. Now, if you remember when we did Gauss theorem, when we discussed Gauss law, phi was what? Phi was 2. 1 you had seen Gauss, according to Gauss theorem, phi is what? 1 by epsilon naught times the charge enclosed. And the formula for calculation of flux was Es cos theta. Now see, if by somehow your theta is 0, not theta, your cos 90 will come out to be 0. So your flux will be 0. So see, because of this phi 2 means flux due to this curved part, this part, what will happen? Area vector is pointing upwards, electric field is directed towards the positive x-axis, making an angle of 90 degree. So this is basically Es cos 90. And cos 90 is what? Cos 90 is 0. So there will be no contribution of flux because of this curved surface. So we have electric field flux due to this first surface and third surface only. So see, if we take the flux due to the first surface plus electric flux due to the third surface, this will give me the net flux of this system. So see, since it is making an angle of 0 degree only, when you will expand, this will be Es flux because of first and then plus Es flux because of second. So your net flux, this becomes 2Es. From your Gauss theorem, you know flux is what? Flux is charge enclosed by epsilon naught. This is from your Gauss theorem. This is from your Gauss theorem. So in the last class, we did continuous charge distribution. So yes, Atif, what was surface charge density?
Q by S.
Q by S. See, we had seen 3 types of charge distribution. One was linear, other one was surface, third one was volume. Linear charge density is charge per unit length. Surface charge density is charge per unit area, and volume charge density is charge per unit volume. So in case of this surface, if we say surface charge density is what? Charge per unit the surface area. From here, I can say Q is equal to sigma S. Now I have the value of charge. If I put it in Gauss theorem, flux will be what? Instead of charge, I can write sigma S divided by what? Epsilon naught. So this is one flux that I am getting. Other flux that I am getting is this. This is 1, this is 2. So both the flux are getting because of this plane sheet only. These are contributed by the same charge. It means these are same flux. So I can equate both of them. So if I equate them, 2Es will be equal to, this is sigma S by epsilon naught. Sigma capital S divided by epsilon naught. Now see, SS means both the surface area, this will get cancelled. Electric field due to infinitely plane sheet will come out to be sigma divided by 2 epsilon naught. All right. Okay. Hiba, you tell me, how is electric field now depending on R? Yes, Hiba. How is electric field now dependent on R? Hamza?
Ma'am, it is inversely proportional to.
Just check this formula now. Just check this formula.
It's not proportional.
It's not proportional. See, it's independent of distance now. In the previous case, when we were studying that infinitely long wire, there R came in the denominator where E was inversely proportional to R. So Hamza, Hiba, and rest of you can see R is not over here. It means electric field, whatever be the value of R, electric field will remain the same. It means it is independent of R. So E and R, the graph will be this, independent. This will show. Now see what kinds of questions you get from this portion. You also get numericals from this part as well. This comes under application of Gauss theorem. So see, majorly there are three kinds of questions that are given to you from this. Basically, what does it do? That it can give you, the question can give you two sheets. Instead of taking one plain sheet, it can provide you with two sheets. Two infinitely plain sheets. And any charge density can be provided to you. For example, let us take positive in this, plus sigma 1, let's say plus sigma 1, and sigma 2 is the charge density over here. Charge density means charge per unit area, surface charge density, and negative charge is given to you. It can ask you to calculate electric field in this region, in this region, in this region. So see, if this is your first surface, this is your second surface. Electric field to be calculated in the first surface. See, this is a positive charge sheet. So look carefully at this. By this only you will be able to solve questions, whatever kind they will come because of this. Electric field due to sheet 1, this is having positive charge. So electric field will be directed away. Directed away will lead us to which direction? Towards the left hand side. Means this will be the electric field due to 1. Then what about electric field at this point due to this? This is a negative charge, so we'll move towards the charge. It means this will be the direction of E2 at this point. First, you will take out the direction. Now see, once you have the direction, you just have to put in the magnitude. E electric field will be what? E electric field, first one, this will be E1 vector plus E2 vector. All right, E1 plus E2. Now see, if I write the magnitude of it, just now we have studied the magnitude is what? Sigma by 2 epsilon naught. So electric field due to 1, instead of sigma, I'll take sigma 1 by 2 epsilon naught. Electric field due to infinitely plane sheet is sigma by 2 epsilon naught. So sigma is sigma 1 by 2 epsilon naught. And what is the direction of E1? E1 is directed towards the negative x-axis. We have seen the direction. It will be minus of I cap. Then plus E2. E2 again, the magnitude is sigma by 2 epsilon naught. So it will be sigma 2 by 2 epsilon naught. And the direction is towards the positive x-axis. This will become I cap. If we talk about this point, electric field due to sheet 1, this will be directed away from it. This will be E1. What about E2? E2 is also negative charge, so it is pulling away electric fields. So electric field will go towards this. It means the direction of electric field will be this only. So now what you have to do, you have to take out the E resultant. E resultant using your simple superposition is what? E1 plus E2. Now if you take up the magnitude, E1 is what? Sigma by 2 epsilon naught. So sigma over here is sigma 1 by 2 epsilon naught, and the direction is negative, a positive x-axis. So this is I cap. Plus electric field 2. Electric field because of 2 is sigma 2 divided by 2 epsilon naught. Direction again it is I cap. Now if we talk about the third surface that we have. Now all of you write me in the chat box, what will be the final electric field? The way I have written it, E1 for E1 for E2. All of you try once. Check out the direction. See the direction, write the magnitude, and just put the vectors I cap, J cap, K cap. Yes, what will be the net electric field? Fatima, Fatima Munir, both are coming in minus I cap, means negative x-axis. Just check once again. Just check once again the answer you have submitted.
Teacher, is it sigma 1 by 2 epsilon naught I cap plus sigma 2 by 2 epsilon naught minus I cap?
Correct. Yes, perfect. Krishna, yours is also right. This will be the answer. See, for all those who are not able to do, first we have to check the direction of electric field. Just remember this carefully because you will be getting question based on this only. For plate 1 is positively charged. For positively charged, electric field is directed away from it. So if this is the point, if I go in this direction, this will lead me towards the plate. So I don't want to go towards the plate. I have to go away from the plate. So this will be the direction of E1, electric field due to 1. E2, this is negative charge. Now I have to move towards the plate. So if I have to go towards the plate, this will lead me in this direction, E2. E2 is what? E2 is now electric field due to plate 2. Now, these are the directions of electric field. Now I just have to put up their magnitude. So E net will be what? E net will be again E1 vector plus E2 vector. So E net, E1 is what? E1 is electric field due to this plane sheet. So this is what? Sigma by 2 epsilon naught is the formula. This becomes sigma 1 by 2 epsilon naught. Now the direction. Direction initially we have specified that this is moving towards the positive x-axis and E2 is towards the negative x-axis. So for positive x-axis we have I cap plus again E2 will be what? E2 is because of plate 2. This will be sigma 2 by 2 epsilon naught. Now the direction towards the negative x-axis, so unit vector I'll write minus I cap. Now see, in your examination, you can get any kinds of plate. You can get both the plates as positive, you can get both the plates as negative, or you can get the similar case, either one is positive or the other one is negative. You can get any region 1, region 2, and region 3 where you have to find out electric field. So the method will remain the same. Wherever you are taking the point, first check the direction for the electric fields. Once you get the direction, write down their magnitude and add the unit vector. In case of your questions, you might get the values of E1, E2. So that will make your work easier to get the final magnitude. All right, is this clear?
Yes, ma'am.
Okay. So just note down this case as well of electric field due to infinite plane sheet. Just write done in the chat box. I'll know when you all have written. Done all? Okay, 1 minute, I'm waiting. Okay, now all of you are done with it. Now the last application of it. Applications we have seen, the last application of this. Electric field due to, now see what all are possible in this derivation. One is hollow conducting. In case of hollow spheres, you have conducting as well as non-conducting. So conducting as well as non-conducting spheres. And electric field due to solid but only conducting. So electric field due to these three all are equal. These three spheres all are equal cases. So we'll do one derivation that will cover all of them. So there are three cases that we get in this. In case of this, we get three cases. Now see, if your point lies outside, if the point is outside, if you have to calculate electric field outside the sphere, so suppose this is the sphere that I have and it has charges plus q outside it. Remember, in case of all these three spheres, hollow conducting, non-conducting, and solid conducting, the charges reside on the surface of the conductor. All right, no charge is present inside. All right. Now see, this is the charge that you have. This is the sphere with the charges that you have. This will be the Gaussian surface now. We take Gaussian surface as a sphere. Why are we taking this? Because this is our point. Let's say this point A. At point A, we have to calculate the field. So at this point is lying outside the sphere. So we have drawn a Gaussian surface at this point. So let's say the radius of this Gaussian surface is small r. And let's say radius of the sphere that we have is capital R. Just wait for 2 minutes. So see electric field outside the sphere. Yes. Now see phi is what? Phi is E dot ds, integral of E dot ds. Now phi, if I write it as E ds means the surface area of the sphere. Now see the surface area that I'll be considering. Be careful over here. You have to consider the surface area of the point that you are taking. Means you have to consider the surface area of the sphere, Gaussian surface that you are taking. Don't consider the surface area of the sphere. Why? Because you are taking the flux within the Gaussian surface. Now this is your Gaussian surface. This is your sphere which you have to calculate. All right. So if the radius is small r and this is a sphere, then your surface area will be 4 pi small r square. This will be the surface area because of the Gaussian sphere. Small r is the radius of Gaussian surface, while capital R is the radius of the sphere. So don't get confused between small r and capital R. Now using your Gauss theorem, you know charge is Q by epsilon naught. This is from your Gauss law. Now let us write surface charge density. So if this is, or let us put it over here, let's equate it from here only. E 4 pi small r square is what? This is capital Q divided by epsilon naught. So electric field is Q divided by 4 pi small r square epsilon naught. You can leave it in this stage also. But if you are provided with surface charge density, sigma. So sigma is what? Sigma is charge per unit area Now see where the charge is spread. The charge is spread over the sphere only, not the Gaussian surface. So when you are taking the surface charge density, you have to consider the radius of the sphere. When we were considering Gauss law, when we were applying flux, when we were calculating the flux, there we took the Gaussian surface's radius, means small r. Now we are taking the charge density, means what is the charge present on this sphere. So you will be considering the radius of this sphere only. So here the surface charge density will be 4 pi capital R square. So Q will be 4 pi capital R square sigma. Just put it in this. Your electric field will be sigma 4 pi capital R square divided by 4 pi R square epsilon naught. 4 pi will get cancelled. Electric field will be sigma capital R square by epsilon naught small r square. This is your final electric field. So this is which case? When your point is lying outside. Now, if I tell you the point is lying on the surface only, calculate electric flux, calculate electric field when the point is lying on the surface only. So if I give you the second case, point is on the surface. So when I tell you point is on the surface means what? This is your sphere. This is the charge. And this is the radius. Now, where is the point given to you? Earlier, the point was given to you over here, outside. Now, the point is given to you at this surface only. So if you draw a sphere, that will coincide with the sphere that you have, means your Gaussian surface will be coinciding with the sphere that you have. All right. So in this case, your Gaussian surface is same as that of the sphere. Is this clear to you all? Why I'm taking the Gaussian surface along with this sphere?
Yes, ma'am.
Clear to all of you or only Krishna?
Clear.
All right. So see, now we'll do the same steps that we were doing. Flux will be what? Flux will be ES. So now instead we don't have any small r over here because small r is equal to capital R only. Both of them are equal. So E will be 4 pi capital R square only. Now you don't need to consider any small r because small r is not over here. Small r was the surface area of the Gaussian surface. Now the surface area of the Gaussian surface is equal to surface area of the sphere. So this is the electric flux that you have. From Gauss theorem, you have Q by epsilon naught. Q can be written as sigma 4 pi capital R square. Now equate both of them. If you write flux, flux will be what? Flux will be charge sigma 4 pi capital R square by epsilon naught. So if I equate both of them, E 4 pi capital R square will be equal to sigma 4 pi capital R square by epsilon naught. So 4 pi R square, 4 pi R square will get cancelled. Electric field will be sigma by epsilon naught. This is the electric field that you get when your point is lying on the surface. Now, the third case that you have is when your point is inside. But see what I have told you. The charges for the conductor are residing only on the surface. There is no charge present within it. So it means if there is no charge present, electric fields will be simply zero. So you don't have any electric field for the solid conducting or hollow non-conducting and conducting sphere when the point is lying inside. So we have done three cases. Let me just summarize this. With the help of a graph, I'll summarize all these points, and this graph is very important, which we will be discussing right now. See, this is your electric field, this is your Gaussian surface's radius. Now, this point, which is the origin, I'm taking electric field at the center. Means I'm talking about the point inside. So at the center, small r is what? Small r is equal to 0. At the center, radius, your small r Gaussian surface is 0. So this point depicts center. Now I have taken another point. This point is equal to capital R. So when your small r is equal to capital R, only at the surface. So this point shows surface. Now from the center of the sphere to the surface, if I take any point, that will lie inside. So when your small r is less than capital R, this will show inside. All right. And if I take any point where Gaussian surface's radius is greater than the sphere's radius, it means the point is lying outside. So this is lying outside. That's how I have considered all the points. This is the center. This is the surface. So why the surface? Because small r is equal to capital R. If I take any point between the center and the surface, that will mean the point is lying inside. So this portion shows inside, and above capital R, it means outside. So now see, if we plot the graph, while recalling the formula we'll do. Electric field from the center till the surface means electric field inside. There is no electric field, this is 0. So there is no electric field present. Then electric field at the surface we did E is equal to sigma by epsilon naught. The second case which we did, this one, electric field is sigma by epsilon naught. So electric field is now independent of it. So you will get some value. This is showing that electric field is independent of R. So this point is what? This is sigma by epsilon naught. So electric field is actually not depending on R over here. Now the very first case which we did, case 1, this was E is equal to sigma capital R square epsilon naught small r square. So E is inversely proportional to R square. This is the point when your point is lying outside. So this shows that point is lying outside, where E is inversely proportional to R square. So you can remember with the help of the graph as well. All right, fine by all of you.
Yes, ma'am.
Now, just note down this application as well. So I think you have written these points, no? From Done? Hanifa, this is your first class, no? All right, so most of you have completed. See, very few topics of your chapter that were left when we were discussing. So I'll be discussing that. So two students, Atif, you and Josefa, am with you. Both, if you wish, you can stay, otherwise you can leave. For you, both the chapter is completed in your previous batch. Electric field lines and torque we are discussing now. So if you want to revise it, you can stay, otherwise it's up to you. Atif and Josefa, both of you. In your batches, it was done earlier. Now see, for the rest of you, let's do some of the properties of electric field lines. Now see, electric field lines, I have told you in very brief that what electric field lines. Okay, Atif and Josefa. So from your next class, new chapters will be. All right. Now see, electric field lines are basic pictorial representation of electric field. Just in order to represent how to represent electric field, we have electric field lines. So electric field lines that we had seen per unit area gave us electric flux, but they have some basic properties as well, which were not discussed earlier. So let us just complete very few topics are left. So electric field lines, these are geometrical. These are geometrical and pictorial representation of electric field line. Of electric field. So geometrical and pictorial representation of electric field is known as electric field line. So basically these are continuous curves and the direction of which is given through a tangent drawn. This is the direction of electric field and this is what is meant by electric field lines. Now see some of the properties of electric field lines. If I tell you, let us discuss some of the properties of it. Now the first property is this one only, that if you have an electric field line, if you have, this is electric field line, and you wish to know in which direction will electric field be. So simply drop up a tangent. So this will give you the direction of electric field for it. So let me write it as well. Electric field's direction is given through a tangent on the electric field line. If you remember earlier when we were discussing fluids, when we had 11th standard, you had fluids lesson. So there you might have studied that two streamlines flow, turbulent flow. So there you must have studied two streamlines never intersect. Similarly, you have this case if you have two electric field lines and they are intersecting. Let's say these are two electric field lines, 1 and 2. Both of them are intersecting. So in this case, electric field lines, if we take out the direction of it, let's say this is the point. At point A, I'm taking the direction because of the first tangent. So if I drop a tangent, because on this electric field line 1, this will be the direction of electric field line. And if I drop a tangent on electric field line 2, this will be the direction. So at the same point, I am having two directions of electric field. So this is not possible. At the same point, I cannot have different directions of electric field. No. So it means these, both of them never intersect with each other. So two electric field lines do not intersect with each other. And if you want the explanation of it, the explanation is simply that there will be two directions of electric field. There will be two directions of electric field. So which is not possible. All right, so this is the first property. The second property that you have is how to take out the strength of electric field line. For example, if I give you this case, these are some electric field lines. You can easily make out two regions are there. One is this region where the electric field lines are very close to each other. Another one is this region where electric field lines are kept at separate distances. So see, from this figure only, you will be able to understand the strength of electric field. How? If let's say this is the direction of the electric field lines in the first region, when electric field lines are close to each other, when electric field lines are closed to each other, that shows that the strength of electric field is strong. You have stronger electric field in this region. And if not closed, close. And if this is close electric field lines, these are kept together, that shows strong electric field. If these are kept far apart, then your electric field strength is weaker. This is your electric field strength is weaker. So from this figure only, if these are the electric field lines, you can easily see electric field in region 1 is stronger than electric field in regions. Simple, easy. You can just figure out using this direction or the separation from it. All right. Now the next property that we have studied a lot of time in flux only. Many of the properties we have studied. This is the third one. So electric field for positive charges, these are directed away in this manner. So for positive charges, electric field lines are away. If you have negative charge, all the field lines will be coming towards the charge. This property we have used a lot of time in electric field in case of electric flux. So if you have negative charges, that gives electric field line, which will move towards the charge. All right. Now see, if you are given positive and negative charges together, in this case only, if I give you positive charge and a negative charge together, so what will happen? See, electric field lines, due to this positive charge, these will be moving away from this charge. And because of this charge, negative charge, electric field lines will be coming towards it. So what will happen? Ultimately, electric field lines will move from positive charge to the negative charge in this manner. Electric field lines appear to originate from positive charge and they appear to terminate at the negative charge. The reason is simple. The reason is the same, because of positive charge, electric field lines are away, and for negative charge, electric field lines are towards. This will be the direction, towards. All right. So electric field lines appear to originate from positive from positive and terminate at the negative charge. Terminate at the negative charge. All right, easy, simple properties. Now, one more property that is very simple is that these are continuous curves. You do not see electric field lines as dotted. So, electric field lines are continuous curves. We don't represent them through dotted lines. Now, see, important properties that we'll discuss simultaneously is lateral contraction and pressures. See, if I have a positive charge and I have a negative charge, this will be the direction of electric field lines originating from the positive and terminating at the negative. So what happens? These, since both of them are getting attracted towards each other, why? Because the electric field lines are moving towards it from positive to the negative. So we call it as they are contracting longitudinally. So electric field lines, they contract longitudinally. This phenomena, contract longitudinally, explains you why attraction of unlike charges occurs. So this explains attraction of unlike charges. We say no, positive charge and negative charge, both of them attract each other. The reason is this only, because of electric field line. Other case that I was talking about, two cases I told you, no. So fifth property is this sixth one. If I have both of them together as positive, so what will happen? Electric field will move away from it. Electric field will move away from it because no negative charge is there. So for both of them, what will happen? For both of them, electric field lines will be moving away. If you take even a negative charge, what will happen? Electric field lines will come from here. There will be no interaction of them. So they will remain continuously at this certain distance, this much distance. So this, we say that they are exerting lateral pressure on each other. So electric field lines also exert lateral pressure. Electric field lines exert lateral pressure on each other, and this explains repulsion of charges. Repulsion of charges. All right. Then one more property, the other next property that we have is seventh one. No. Yeah, seventh. So this property says that if you have a neutral point with you, let's say these are some electric field, this is the neutral point. So neutral point is what? We have done questions also on neutral point when we were discussing electric force, when we were discussing electric field. So where the net electric field was 0, that was the point, neutral point. So electric field lines never cross through this point. They can move away from it, but they are parallel to it. Basically, the electric field lines are parallel to it. Electric field lines are parallel to the neutral point. They are always parallel to the neutral point. So they cannot cross it. They cannot cross it. Okay, so they cannot cross it. And the last property that we have, if you are given a surface of a conductor, for example, this is a conductor. So if you have a conductor with you, electric field lines, remember, they cannot go through the conductor, means they cannot penetrate the conductor. Electric field line will stay perpendicular on the surface of conductor. electric field lines cannot go through the conductor. That's why in the case when we were discussing sphere, electric field came out to be 0 inside the conductor, because electric field lines are not able to move inside it. And the other reason was that charges reside on the surface. So this is that same only. So electric field lines are perpendicular on the surface of conductor. Electric field lines are perpendicular on the surface of conductor. So remember one thing, that they cannot penetrate it. They cannot penetrate it. Okay. Now one more thing, when I was telling you about when a positive and negative charge is kept together. So remember, if positive and negative charges are kept together and both of them have different magnitudes. Let's say Q2 is greater than Q1. You have Q1 with you, you have Q2 with you. Both of these are positive charges. And if I give you a condition, Q2 is having the magnitude greater than Q1. So always remember, neutral point lies to the near the charge which is having the lesser magnitude. So this will be your neutral point. So electric field lines will be parallel to it in this manner. In this, and
Teacher,
since
I
at
understand this one.
this point, Fatima,
Yeah. Yes.
see, let me draw it again. You are given two charges, plus Q1 and plus Q2. All right. Now see, as I've told you, both of them are positive. If you have two charges which are in the same, having the same sign, what happens whenever you get the neutral point? The electric field lines are directed parallel. So now, where to locate the neutral point if the magnitude is not same? See, if both of them have the same magnitude, the neutral point will be simply in the middle, the way we have done it for electric field. But see, if the both of them are not having the same magnitude, where will you put the neutral point? Towards Q2, towards Q1. There should be some basis of it, because you cannot put it in the middle of it by yourself. No. So if it is having both the same magnitude, both of them are having the same magnitude, then you can put the neutral point in the middle, because the neutral point will be in the middle only. But if I give you some case where Q2's magnitude is greater, remember that neutral point, this lies near the charge having lesser magnitude. So from Q2 and Q1, Q2 is having the lesser magnitude. So neutral point, instead of lying in the middle, it will lie somewhere here. This will be the neutral point. Inclination towards the positive Q1. All right. So if I draw electric field line for Q2, these will line move away from the charge. For Q1 also, this will move away. But at the neutral point, they won't be crossing. There will be no electric field line at this neutral point. So for Q1 positive, it will move away. For Q2 positive, it will move away. These will be the directions of electric field lines. Now is it clear?
Yes, teacher. Thank you.
All right. So these are some basic properties of it. All right. So note it down as well. Note down the properties of electric field lines.
Ma'am, can you show the fourth point again?
Yes, yes, sure. Yes, completed.
Yes.
All right. Now see one question that usually comes in your exam, which we have not discussed. See a proton. Whenever the charge is kept in external electric field. So proton and an electron, these are placed at rest near positive and negative plates. You have to calculate time taken by electrons and protons to reach other end. These are the two plates that are given. So one is positively charged, other one is negatively charged. So electron is here, proton is here. Now see what is meant by the question. See, electrons are released, protons are released. Both of them reach the opposite end. So in these kinds of question, you have to solve it through your concept of force and electric field, which we did. See, electric force on a proton, let's talk about proton. So electric force on proton will be what? If you remember, it is QE. And also direction of electric field for positive charges away, for negative charges towards. So this will be the direction of electric field. Let's say this separation is small d. If proton is a proton, you know it's a positive charge. So for positive charges, direction of force is same as that of electric field. So direction of force on proton will be this. All right, so F is equal to QE. If MP is the mass of proton, then acceleration will be what? Acceleration is F is equal to ma. So acceleration is F divided by m. So acceleration of proton will be F by m. F is what? QE. M is mp. So this is the acceleration that you have. Now see, initial velocity is 0. Recall all your 11th standard first lesson, motion in 1D. Initial velocity is 0. The distance that it has to cover, can any of you tell me what is the distance that the proton has to cover?
D.
D, correct. This is the distance that the proton has to cover, which is small d. So distance is small d. Time, I have to calculate time period. Acceleration of proton, I have calculated QE by mp. Now if I apply equation of motion, ut plus half at square. So this will be for proton, up, tp, ap, tp. So what is this? This is 0. So sp is, this term will be 0. sp, it is given as small d. So small d will be equal to half a. A is QE by mp t square. TP square, which I do not know. What is TP square? I have to calculate them. So from here, TP will be equal to what? TP will be equal to 2, and TP square will be equal to 2 MP small d divided by QE, and TP will be equal to 2 MP divided by QE under root. This will be the time period for proton. Now, if I have the case of electron, what will be the difference or what will be the change that will come? Instead of taking the mass of proton, I'll be taking the mass of electron. Rest of the quantities are same. See, initial velocity for electron is also 0. Let me write it separately. initial velocity for electron is 0. The distance that electron has to cover, it is also d. Time for electron is te, which I have to calculate acceleration of electron. Instead of writing qe divided by mp, now I have it as me, where me is the mass of electron. Me is the mass of electron. So I'll get the same result. It's just that instead of writing mp, I'll be having 2me small d divided by q capital E under root. This will be the time period. So whatever kind of question you will be having, you can put in the values. This is how you solve these kind of questions using your equation of motion. All right, so note down this question as well. Yes, class done.
Yes.
Done, ma'am.
Yes.
All right. Now see one last topic that is last topic of today's class, as well as it is last topic of this lesson also. Torque was left. So see, before discussing torque, you have to have a bit knowledge about cross product. So see, if there are two vectors, vector A is there, vector B is there, making an angle of theta, then A cross B means cross product of A, B is given by magnitude of A multiplied by magnitude of B sine theta and unit vector n cap, which shows the direction. And direction of A cross B is perpendicular to both A vector and B vector as well. And if you have to find out the direction, just write I, J, K, I cap, J cap, K cap, and start moving. From I to J, if you move, I cap dot J cap, this will give you the third one which is left, that is K cap. And if you reverse it, means if you write J cap into I cap, that will give you minus of K cap. Then if you move from J to K cap, J cap cross K cap, that will give you what is left, I cap. And if you move reverse of it, K cap cross J cap, that will give you minus I cap. Last one, K cross I, K cap cross I cap. What is left? J cap. And if you take the reverse of it, I cap cross K cap, that will give you minus of J cap. That's how we solve. This is the basic of cross products that you have already done. Apart from this, one thing you have to remember, if you have two vectors, if you have two forces, this is force 1, this is force 2, F2, and both are having the same magnitude, F. This line where both the forces are acting, this line for this F1, this line for this F2, this is called line of action. This is called line of action. These forces are perpendicular. Let's say the separation between them is small t. All right. So if two forces are equal and opposite, two equal, opposite means opposite in the direction, two equal and opposite forces. You call them as a couple. They form a couple. So two equal and opposite forces which are directed in the opposite direction. Opposite means opposite direction. All right, magnitude is same. Now electric dipole, if it is kept in a uniform electric field. Let's say this is uniform electric field. All these are electric field lines. I have taken a dipole. This is a dipole. Plus Q charge is there, minus Q charge is there. This forms a set of dipole. Let's say the separation between the charges is 2A. Now see the net force on this. Net force will be what? Force due to this. This is directed in this direction towards the electric field. Why? Because for positive charges, the electric force is directed in the direction of electric field. And for negative charges, wherever is the direction of electric field, reverse it. So if this is the direction of electric field in the right hand side, reverse it. So this will give you force for the negative charge, minus Q. This will be force because of plus Q. So net force will be what? FQ plus QE minus FQE. That will get cancelled. That will be 0. So net force is 0. Now see, if we talk about torque, torque you remember from your 11th standard, in your rotational classes you must have done. Torque is a rotational analog of force. In rotation, instead of writing force, we use torque. All right. Now see, in this, for torque, torque's basic formula is R cross F. R is the perpendicular distance, F is the force. So see, now if I am taking torque, if this is the line of action, see, this will be the line of action now. I've told you what is the line of action where the force acts. So see, I have to drop up a perpendicular. So if I drop up a perpendicular, let's say this point is N, this point is A, this point is B. All right, I have drawn up a perpendicular. Let's say this is theta. This point is theta, this is the perpendicular. Now, according to the definition of torque, I require this R, I require this F. This I am not aware of. So what can I do? I can simply use sine theta. Now see, if I use sine theta in this triangle, sine theta is perpendicular divided by hypotenuse. Perpendicular is this BN. This is the perpendicular divided by the hypotenuse, that is 2a. So Bn is what? 2a sine theta. BA, this is 2a sine theta. Now see, what is Bn? Bn is actually the perpendicular distance that I have taken. It means now I have got the value of my R, which I didn't know earlier. So see, torque will be what? Instead of R, I can write 2a sine theta. And for the force, I have QE. So torque is what? Q into 2a E sine theta. Can anybody of you tell me what is Q multiplied by 2a? Yes, Fatima?
Dipole moment.
Dipole moment. Dipole moment was Q into 2a. So torque is what? Torque is now P, that is the dipole moment, E sine theta. Or torque can be written as whenever you have two vectors multiplied by sine theta, that gives you cross product. So this is P cross. Your torque is P cross. All right, just note it down. If anybody wants to write this cross product, you can write. Just let me know. Then this is your cross product from your 11th standard only. See, if I give you three cases for it. Case 1, case 2, and case 3. All right. If electric field, this is the direction of electric field for all the three cases. Now the difference that will come will be in the direction of dipole. First, this is the direction of dipole. In second case, I am giving you this direction of dipole. And in the third case, this is the direction of dipole moment. Now see, if you look at this carefully, this is making theta is what? What is the angle in this first case?
0 degree.
0 degree.
In the second case?
180 degree.
180.
And in the third case?
90
90
degree.
degree.
90 degrees. So only Fatima and Krishna know these angles. The rest of you are not aware of the angles. Now see, if I put the values of the angle, T, PE sine 0, that will give me torque as 0. And F net, as we have already discussed, force net is already 0. So this is a condition of stable equilibrium. Why stable equilibrium? Because the dipole will try to align, the torque will try to align the dipole in the direction of electric field. So it is easier for it. So this is stable equilibrium. Now see, torque PE sine 180, this is also 0. And F net is already 0. But see, this is, in this case, electric field is directed away from it. In this manner, both of them are directed away. So torque will have to do more work to align it. So it's a condition of unstable equilibrium. If you disturb it, the dipole will not return to its original position. So this is a case of unstable equilibrium. When your dipole is making an angle of 90 degree with the electric field. So this is PE sine 90, where torque is equal to PE. So this is the maximum value of torque possible. And force will be 0. Force will still be 0. So this is not a complete your equilibrium. You only have translational equilibrium. No rotational equilibrium because torque is not there. All right, so note this down as well, and let's do one numerical formula based question on this. Till the time just write once, all of you. This is formula based question. 2 plus 2 millicoulomb minus 2 millicoulomb are separated by 3 millimeter. So calculate the dipole moment. You have the angle, you have the value of electric field. Quickly tell me what is the answer. All of you should respond now, not only Krishna and Fatima. Rest of you also submit your answers quickly. And if you get the answer in terms of root, no need to solve it, write in terms of root only. Just submit it. Yes, answers. Answer everyone. Akifa, Fatima, Hamza. Others also submit. Only 2 students have given their answers, Krishna and Akifa. Hamza, you also answer. Hiba, both the Fatima. All right, then let's discuss it if no more answers are coming. So the correct answer has been given by Krishna. Correct, Krishna. See, let us discuss this. What is torque? Torque is PE sine theta. Now, do we know P? We don't know P. We have to calculate dipole moment. Dipole moment is given by charge multiplied by their magnitude. Hiba, now answer. What is the charge that I should take? Hiba.
-2.
-2. Only -2 coulomb. There's something else with -2 as well. Just look it. It's not -2 only. See, the charge is 2 millicoulombs. charge is given to you as 2 millicoulombs. And see, you don't take minus and plus when you are considering dipole. All right, just take one of the charges magnitude. 2 millicoulomb, take it as 2 millicoulomb. And millicoulomb, don't ignore this milli. You have to convert it into SI unit, 10 to the power minus 3 coulomb. This is your charge, not dipole. This is your charge. Hamza, tell me what is 2A in this?
Ma'am, 3 mm.
3 mm, correct. This is 3 millimeters. So 3 millimeters have to be converted into the SI unit. This will be 3 into 10 to the power minus 3 coulomb. So now I have Q, now I have 2A. I can get the dipole as Q means 2 into 10 to the power minus 3 multiplied by 2A, which is 3 into 10 to the power minus 3. So this gives 6 into 10 to the power minus 6. I have the value of P. What is the value of E given? E is already given to you as 10 Newton per coulomb. E is already given to you as 10 Newton per coulomb. Yes, Fatima, what is the angle that I should take?
60 degree.
60 degree, correct. So the angle theta is 60 degrees. See, all the data are kept over here. Everything is here. You just have to put it in the formula. Torque will be P, 6 into 10 to the power minus 6, E, 10, multiplied by sine 60 degrees. So torque will be what? 6 into 10 to the power minus 5. So this is 6 into 10 to the power minus 5 multiplied by root 3 divided by 2, value of sine 60 degree. This will be 3 root 3 into 10 to the power minus 5 Newton meter. All right, here to all of you. Fatima, Munir, Hamza, Hiba, Hanifa, is it clear?
Yes, ma'am.
Yes, ma'am.
Just note down the solution. Just write done when you all have written it down. Write it in the chat box. All right, so most of you have written. You are all done. Okay, fine. So this completes our first chapter. This brings us to the end of the first chapter. So please revise this chapter. Now you will be soon having a subjective test of electric field and charges. So please keep on revising this. And in the next class, we'll continue the next chapter. All right.